Welcome to Lecture 4A entitled Partial Derivatives. The material for this lecture comes from section 15.3 of the text. The objectives of this teaching module are to know how to compute the partial derivatives of a multivariable function. And the concepts and definitions that will be developed are the notion of partial derivatives, and also now to make a distinction between a partial derivative and a direct derivative. All right, as usual, the second slide is just an outline indicating what we will cover in the subsequent slides. I'll just have you, the class, read over the individual items, and we'll just move forward from here. All right, so before we get into the actual mathematics, in terms of what is a partial derivative and how we compute it, let's give some motivation for this. And that is particularly a problem, for example, where you have a hiker who is basically hiking along a mountainside, up or down or sideways. So if you look at the picture on your right, you basically see pathways that hiker can take. And what you'd be interested in knowing is, depending on the path taken, what is the slope that the hiker sees as a function of position along the chosen pathway. And so, for example, here it's clear that the slope gets increasingly large, and then all of a sudden the slope is 0 at the top, and then it becomes negative as you go down the hill. On the other hand, if the hiker goes to the right, they're going downhill, and then on the other side also going downhill. And so depending on the direction in which you go, the slope will be different. Mathematically, we could take this same diagram and basically draw the picture that you see on your left. Now the hiker is sitting in this little saddle point here, which is right at the top. And so this point here would be designated as position 0, 0. And this would be some functional describing the shape. And that would be the z component, which would be evaluated at position 0, 0. All right, so this is a mathematical description, but what we'd like to do is to calculate what the slope is as the hiker goes on a specific path. Now, the actual problem itself will not be solved until Lecture 6, but for the time being, we need to develop the necessary tools so that we can actually solve this problem. All right, so first thing is to basically start with definitions. And what we'd like to do is to go back and look at what you learned last year regarding single variable problems. What is the definition of a derivative? Well, there's only one variable, so there are no distinctions to be made. And because of that, we say it's a direct derivative. And the definition would be a limit. It's a limit where you're evaluating the function at some distance slightly larger or smaller than the point of interest, minus the value at the point of interest, divided by this small distance h, and then you let h go to 0. All right, so this particular derivative will exist provided the limit exists. So how do we distinguish now between the single variable case and the two variable case? Well, in the two variable case, we now basically have some ambiguity because the hiker, or whatever you want to call it, it has 2 degrees of freedom. You can move in the x direction or you could move in the y direction. And so you can talk about a derivative with respect to x or a derivative with respect to y. So the derivative with respect to x will be a partial derivative, and the derivative with respect to y will also be a partial derivative. So partial with respect to x, partial with respect to y. And this will be evaluated at some point a, b. And so if we're taking the partial derivative with respect to x, then we're evaluating x at a plus h, b is held at some constant value, minus the function itself evaluated at a and b divided by h. Similarly, if we're dealing with the partial derivative with respect to y, then what we're doing is perturbing the y component, so this becomes b plus h minus f of a of b divided by h. And both of these basically exist, provided the limits exist. So these are the only distinction now that we're basically using the same definition for derivative, but now we basically have 2 individual derivatives, and we call them partial derivatives. So just as a note, when you take the partial derivative with respect to x, you hold y as a constant. Likewise, when you take the partial derivative with respect to y, you hold x as a constant. Notice the similarity between the definition of the partial derivative and the direct derivative in 1D. All right, so let's now look at each one of these in turn. This is a partial derivative with respect to x. And so we have a number of pictures here. The one on the top left is just showing what the function looks like, a function of x and y. And this is basically to look at now at some position a, b, and b basically being the y value. And so this value is held fixed. And if you were then to draw a plane, which is representing the case where y equals b, and this slightly orange color indicates the plane, and we are basically picking off a level curve, which is this one shown in black. And what we're interested in doing is basically finding the partial derivative at this location here. Well, the starting process is to work with the limit definition. And so in the limit definition, we would have the function evaluated a plus hb, which would be this point here, minus the function of evaluated ab, which would be this point here, divided by h. Well, this represents a straight line or connecting these two dots, which both lie on this curve. Now, in the limiting process, what will happen is at this point will slowly but surely slide in this direction until eventually we end up with a picture on the far right, which is this red line. This is in the limit, and this becomes the line which is tangent to this curve at the point a, b, and function evaluated at ab. So this is the definition of the partial with respect to x. This is a pictorial representation of that. All right, you can also look at an interactive version of this. If you click on this link, I'll leave it to you to play with it just to get some idea as to what is going on when we take partial derivative with respect to x. All right, we can repeat the same process, but now looking at the partial derivative of f with respect to y. In this case, basically, what we're doing is we're holding x constant and letting y vary. In this case, x is held at a, and so that means we end up with this plane, which is basically in the z direction, and this intersects the surface to form this level curve that you see here that passes through the point AB, FA of B. So again, we basically apply the definition for f partial y, which means we evaluated y at slightly larger value, that is at b plus h, and then we subtract from that the function evaluated at ab. And the difference of those two divided by h in the limit becomes the partial derivative with respect to y. So here, for instance, you see the dot representing the function evaluated at a, b plus h, and here you see the function evaluated at a and b. And the line between these two basically passes through these 2 points. In the limit, this point is slowly moving down this curve until eventually it touches this point here. And on the right, you see the limiting process. This will give you a line, or we call the tangent, to the curve at point AB, and then Z evaluated at point AB. But this is a line basically now which is parallel to the y-axis in this case. That's the pictorial representation of the derivative of f with respect to y, that is the partial with respect to y. All right, again, if you want, you can look at this interactive figure, which is provided in the textbook if you want to sort of look at some interactive issues. All right, so now let's look at the process of doing the calculations. And so the first thing we want to do is to take the partial derivatives from the actual definition itself. So we start with the expression here, f of xy of x squared y, and we want to compute df dx and df dy. So for df dx, basically, we just maintain y constant and perturb x. And so we take f of x plus h and y, and we substitute into this expression, and then f of xy substitute, which is just x squared y, subtract the two, and then basically grouping the terms, you basically just square this out. And then you'll notice here that x squared and x squared will cancel, and you're just left with 2xh plus h squared, but you have a common h here, so you can bring an h out, and then the h's divide, and you end up with 2xy. H is basically out of the picture here in the sense that as h goes to 0, the only term that's left is 2x, so you end up with 2xy. For f partial y, basically we perturb the y value, so this becomes y plus h minus fxy. So again, what we would do is we would plug in y plus h in here and x, and then do the calculation that's shown here. And here we basically end up with an expression that looks like this, but notice that y and y cancel, and so you're just left with h over h. That cancels, and you're left with just x squared. So f partial y is just x squared. So this is the example that we're looking at with respect to calculations using the definition. So now let's basically do it in terms of just treating one of the variables as a constant. So for example here, f partial x would mean that y is maintained constant. So by taking the derivative of this expression with respect to x, y can be taken outside because it's a constant. So we're taking derivative only with respect to x, and we get 2xy. If you then want to evaluate at a given point, 1, 2, then you would take the final expression and basically substitute the value 1 for x and 2 for y, and you end up with a value of 4. If you take the partial with respect to y, then in this case x squared is a constant, so you can bring it outside the derivative. And we're just taking the derivative with respect to y, and we end up with x squared. And again, we evaluate this at point 1, 2. Well, there's only an x factor here, so that means we evaluated at x equals 1, and you end up with a value equaling 1. So this is basically calculating the partial derivatives, but just treating one of the variables as a constant. All right, so now let's look at more complicated arrangements, computing partial derivatives using the product rule. Suppose we have this function here, which is a combination of two functions, x squared and e to the xy, and we want to compute dg partial x and dg partial y. And so we would basically, in this case, for instance, take the derivative of this times x squared, take the derivative of x squared, and then maintain this constant, so this just becomes e to the xy. So you can see the two terms here, and this is basically nothing more than product rule. So this is just a matter of now taking a derivative with respect to x, and so this y is treated as a constant, y comes outside, and it's ex to the y. Here, derivative with respect to x squared, this just becomes 2x exy, and then you can simplify terms until finally you end up with this expression. Again, in this case, y was held as a constant. If you take the partial with respect to x, it was partial with respect to y, right? Then you're basically only seeing that there's one term involving y. X squared is a constant, and so we end up with the expression as shown here. All right, we could now also consider taking higher ordered partial derivatives. In other words, second derivative with respect to x, or derivative of x followed by the derivative with respect to y. Now this would not have occurred in the case of one variable, because in the case of one variable, you just have first order derivatives and second order derivative and third order derivatives always with respect to x. But here now we have two variables to consider. We can take a derivative with respect to x or y, any combinations thereof. So the expression shown here basically shows the number of partial derivatives. How does it scale? Well, it scales according to m to some exponent n, m being the number of variables, and n is the order of partial derivatives. So if we're dealing with first order, that means n equals 1, and if there's one variable, m would be equal to 1. In our particular case, we're going to look at two variables. That means basically m is 2, and we're interested in second order. So that means n would be 2, which means this would be 2 to the power of 2, which means there are 4 possible combinations of second order partial derivatives. And what we've done is spell them out here. There are different ways of doing it. This is where we basically just spell it out in detail, all the different combinations we can consider. And this is sort of a short form, shorthanded form, f partial xx, f partial yy, f partial yx, and fxy. Those are the only combinations that we would be considering if we're dealing with second order derivatives. This is just things saying things in words. You know, you can write it out this way as well, say it out in these ways. Anyway, so this is more or less nomenclature we'll be using when we start taking derivatives of higher order. All right, so let's do an example. Compute the second partial derivatives of the function 3x to the power 4y minus 2xy plus 5xy cubed. So the first thing we need to do is to take the partial of f with respect to f and partial with respect to y, which is what I've done on this page. So here basically, again, because of the product rule, you've got the product of two variables. Mind you, when you're taking the partial derivative with respect to x, y is treated as a constant. So when you take the derivative with respect to y, it's basically a 0. So it's only y can come out, and you're taking the derivative with respect to 3x to the power 4th for this term, just x this term, and x this term. And when you do this calculation, you end up with this result. F partial y, basically, in this case, y is the operative, x is treated as a constant, so the 3x to the power 4 can come out as a constant. In this case, 2x can come out as a constant, 5x can come out as a constant. Again, by product rule, we end up with this value for the f partial y. All right, so I've just put them up here. F partial x is this, f partial y is this, and now we want to take second order partial derivatives. So we could take the derivative of this with respect to x. We could also take derivative with respect to y. We can take derivative of this with respect to x and also derivative with respect to y. So we end up with 4 different combinations. So if I take derivative with respect to x of df dx, that is basically working on this expression. You can do this yourself and show that it's 36x squared y. If I take f with respect to y and take another derivative with respect to y, which means I'm taking the expression for f partial y, which comes from here. And if I take derivative with respect to y, of course, that means x is held constant. This will just become 30xy. Okay, so the last one would be if I'm taking the derivative with respect to y, followed by derivative with respect to x. Then I'm taking f by y, which comes from here. And now I take the derivative of this expression with respect to x, holding y constant, and I end up with this expression. Let's reverse the order. Let's take df dx, which is from here, and then take the derivative with respect to y. In that case, x is held constant. You take derivative with respect to y. You end up with this expression. And lo and behold, these two are exactly equal to each other. In other words, the ordering doesn't matter. You end up with the same result. But that begs the question, is it always the case? Well, the next theorem will answer this question. This is basically the equality of mixed partial derivatives theorem, also called Clairaut's theorem. And so it essentially says that assume f is defined on an open set D of R2, and that fxy and fyx are continuous throughout domain D. So that's the main condition, that it's continuous. Then fxy equals fyx at all points of D. You can extend this theorem to higher derivatives. So for example, if we have third order derivatives, you'll notice here that you have x, y, x, so 2 x's and 1 y. You have x, x, y, again 2 x's and 1 y. And here you have again 2x and y, but we've just changed the order of integration. So in this case, these are all equal to each other if all 3 partial derivatives are continuous. And of course, this can be extended to higher derivatives. Generally speaking, the problems that we'll be dealing with will be of a nature where it'll be sort of immediately obvious that we're dealing with partial derivatives which are continuous. So you just keep that in mind. That concludes lecture 4A. Thank you for listening.